questions, don't hesitate to ask. Okay, so let's take a look at this practice quiz for our final exam of Organic Chemistry 2. The first question says, onto which of the numbered atoms in the following structure can the negative charge be moved by drawing resonance structure? So I'm going to have to switch over to a blank document for this one in order to draw all of the resonance contributors. So I'll just give you a second to look at it, and maybe you've printed it out, maybe not, I don't know, but that might be handy. But we have the negative charge on the oxygen right here, and we're going to see where else we could move that around. Now, obviously, we could start by drawing a resonance structure like this, so we know it's going to end up on number 6. So if it's going to end up on number 6, that means that B and C are possible answers, and we can scratch off A and D immediately. So why don't we just go see if it can land on all of these other places, on 2 and 4. And I guess really the question only becomes, is it going to end up on oxygen 8 or not? And I think we can figure that out pretty quickly. So let's go over to a blank document quickly. And let me see here. If I wonder if we could draw all the resonance arrows. If we did this, then this, and this, and then this. Oh, look at that. So you do end up with a negative charge on the oxygen that's numbered 8. Okay, so that means that the answer must be C. And if you don't believe me, let's go to a blank document quickly and we'll draw it. If you're like, that's too many resonance structures in one fell swoop, Mr. Dion, that's no problem. We could take a gander here. So if we redraw the molecule the way that they have it drawn, so they have the oxygen with the negative charge here. There's that oxygen. This is oxygen number 8. Then we have this one over here. And of course, we saw that it's going to end up on carbon number 6, right? Because we could draw the first resonance contributor like this, where we end up with a negative charge over here. So I'm just going to draw a resonance arrow like this. And I think I'm going to try to copy and paste this to actually save some time. So copy this, paste it right here. Just going to edit my structure ever so slightly. So let's do this and this. There we go. So now we have our negative charge removed from here, and we have it over here. And again, this is carbon number 6. And of course, we can draw another resonance contributor where we put that negative charge up here. And that is carbon number 4. So let's do that. And let me draw another resonance arrow here. And I'll use my paste again, and we'll just fix up this structure. So let's see, let's erase all this, erase this. So we're going to have a double bond here. We're going to have another double bond here. We'll have our lone pair up here like this. And now the negative charge is on carbon number 4, or atom number 4, I could say. And then, we can't draw any resonance structure where the negative charge gets up to the oxygen numbered 7. However, we can delocalize this pair of electrons over here. We could move this double bond here, and we could push the electrons over here onto the oxygen numbered 8. So let me just draw what that would look like quickly. So I've got all these double bonds in conjugation. I've got this aldehyde over here. Got a double bond here, negative charge like that, and this in a lone pair. And again, this is the oxygen that is numbered 8. And so the answer is what was it? Yeah, I didn't draw the resonance structure where the negative charge is on carbon number 2. We could do that quickly if we just drew this here and this here like this, and then you would see. So if we take this, I kind of skipped one, didn't I? Anyhow, you get the idea. So we'll put this one here. We'll make sure to draw a new resonance arrow, and we'll fix this up. So now we've got the negative charge moved over to here on this carbon, and that is carbon number 2. So there you go. Those are the resonance structures that we need. And by now, I figure at the end of Organic Chemistry 2, my students are pretty rock solid at drawing resonance structure. So And I showed you a really fast way to kind of solve that just by, doing it very quickly. And so the answer is C for the first one. All right, let's move on to question number 2. It deals with pKa values. It says, which of the indicated protons in this compound would have the smallest pKa value? I'm going to throw that out there to my students who are in the chat right now. Excuse me. Does anybody have an idea which one of these would be most acidic? Most acidic. So how would we do this? You remember Aereo? Atom, resonance, induction, orbital. So if you were to remove any one of these protons, they all end up on a carbon. So we can't differentiate using atom. If we were to try to draw resonance structures, well, for some of them, we could technically draw a resonance structure, but others we couldn't. So we can't really use resonance to differentiate, and we can't use induction because there's no special inductive effects, but we could use orbital to solve, couldn't we? Right, because on number 1, or A, sorry, this carbon is sp2 hybridized, and this carbon here on C, this one is also sp2 hybridized. Now for B, the carbon is sp3 hybridized, and for C, the carbon is sp hybridized. So we go with orbital. Now which one of these has the smallest hybrid orbital? The answer is the sp hybrid orbital. So an sp hybrid orbital, this proton has a pKa of around 25. Okay, whereas the ones that are sp2 hybridized, they have pKa's around, I don't know, 40-ish. Okay, and then this one here, the benzylic ones probably also have pKa's that are close to 40 as well. So I'll put around 40 for this one. And vinylic, that's going to have a really high pKa as well. But remember that we saw very often in organic chemistry that you can have an alkanide ion, right? You can produce an alkanide ion very easily just by treating this with sodium amide, right? So this is definitely going to be the most acidic proton, and therefore it has the smallest pKa value. So smallest pKa value means most acidic. There we go. Let's move on and talk about number 3. It says, which Newman projection represents the most stable conformation of this compound? So this is what? This would be 1, 2, 3, 4. So this would be, let's see. Let's draw the compound out and see if we can figure this out. So this would be what? 2,3-dimethylbutane is what it is. Okay, so this compound here is 2,3-dimethylbutane, and we're looking for the most stable conformation. So we've essentially got this compound. We've got 1, 2, 3, 4. We have a methyl group here and a methyl group here, and you would look down this carbon-carbon bond for the most stable conformation. Without even, going to a blank sheet. Does anybody notice anything problematic about any of these? I noticed some issues here right away. But does anybody notice some big red flags here? I'd say there's 2 that have a major red flag. So this is 2,3-dimethylbutane. Okay. So somebody says, what is it? A has lots of steric hindrance. Yeah, you have steric hindrance here and here and here. Yeah, so you have a lot of gauche effects. Yeah. So we have what? 1, 2, 3 gauche interactions here. 3 gauche interactions. The problem with D, I don't know if anybody noticed this, but look, if this is a carbon here, it's got 3 methyl groups attached directly to it. So this is a tert-butyl group. There's no tert-butyl group in the molecule. And in this carbon in the back here, this carbon is attached to 1, 2, 3 methyl groups. So this is also a tert-butyl group. There are no tert-butyl groups in the compound. So it's not even the right molecule. It doesn't even have the correct connectivity. Both A and C represent 2,3-dimethylbutane. But yes, you can see that there's 3 gauche interactions in A, whereas in C, it has only 2 gauche interactions. And so C is going to be the most stable conformation because it has the least gauche interactions, not ghost interactions, gauche interactions. But again, B and D aren't even the right molecule, so that's way off in left field. Well, let's move over to number 4. Which resonance form best explains the greater acidity of paranitrophenol to phenol, right? So if we just draw plain old phenol, that would be this compound, okay? And if we draw paranitrophenol, that would be this. Now we know that the pK of phenol, the pKa is 10, right? That's one of the pKa's that we would have learned in Organic Chemistry 1. But we know that the pK of paranitrophenol must be less than 10, right? It must be more acidic. Now, if we go back to Areo and we think of the conjugate bases, all of which are drawn here, right? We have a negative charge over here. We have an overall -1 charge here. We have an overall -1 charge here, and we have an overall, well, this one's neutral, so that's definitely not going to be the answer. So we're going to cross D out immediately because it's not a conjugate base, right? It doesn't have a negative charge. But we can't use atom because the negative charge would end up on an oxygen in both cases. However, we could use resonance, right? Because a nitro is going to be able to take on that negative charge, right? And so we're going to have more resonance contributors for paranitrophenol than we would for phenol, right? If I just draw the conjugate base of paranitrophenol, so I'll draw it out here, and this is the phenoxide. So we'll put in our 3 lone pairs here, and we'll draw the nitro group out explicitly. Well, since the nitro can take on that negative charge, so I'll use a different color here, we can draw that resonance contributor where we show that negative charge being delocalized down into the nitro group like this, okay? And that's going to give us this resonance structure. So let me just draw it down here. We're going to end up with something that looks like this, where we still have a positive charge on our nitrogen, but now both oxygens have a negative charge. And so we've delocalized that negative charge down onto the oxygen. And so the answer must be C, because it actually shows the delocalization of that negative charge down into the nitro group, right? There we go. So the answer is C, right? C right there. Okay, let's move on to 5, and it says which molecule has the R configuration? That means that 4 of them are S, 1 of them is R. I'll give you a second to look at it, and I'll see if somebody can come up with an answer. While you're doing that, I'm going to a sip of water. All right. Somebody says C, I think. Well, let's take a look. We'll start with A. I'm going to go a little bit fast here. So in A, the oxygen has first priority. Hydrogen is the loser. This carbon is attached to 2 oxygens, and this one is attached to 3 hydrogens. So there we go. So we go from 1 to 2 to 3. Like, sorry, I went the wrong way. I was like, that's not right. So we go from 1 to 2 to 3. And so this one has the S configuration. If we go over to the next one, B, the hydrogen, again, is the lowest priority. Oxygen is highest priority. This carbon is attached to 3 oxygens. This one is only attached to 1. So we go from 1 to 2 to 3, which again is counterclockwise. And so this is also S. We're going to skip C since Skylar thinks that might be the right answer. So we'll go over to the next one, which is D. This is going to have the lowest priority. This has the highest priority. This is number 2. This is number 3. So we go like this, which is also S. And if we go over to C, I'll use the green pen. The hydroxyl is going to be number 1. This will be number 2. This carbon is attached to oxygen and 2 hydrogens, so this is number 3. And the methyl group is lowest priority, and it's facing away from us, so it's number 4. And we're going 1 to 2 to 3, which is clockwise, and so this one is R, so the correct answer is C. It's the only one that's R. And there you have it, a little practice on your Kohn-Ingold Prelog rules. If you need to review those, the Kohn-Ingold Prelog rules for assigning stereochemical configuration. Number 6, it says, what is the stereochemical classification of 1s, 2s, 1,2-cyclohexane diol, and 1r, 2s cyclohexane diol? Can anybody answer that quickly? They're the same at one stereocenter, but they have the opposite configuration at the other stereocenter. So what would the relationship be? Yeah, they're diastereomers, aren't they? Right? If they were enantiomers, an example of that would be if you had 1s, 2s, and 1r, 1r, 2r. Those would be enantiomers, for example. All right, here we go. Let's move on from there. On to question 7. It says, which of the following is capable of exhibiting cis-trans isomerism? So we've got 4 compounds here. A is an alkyne, and the molecular geometry at the sp hybridized carbons is 180 degrees. Right? This one is also 180 degree bond angle. And so there's no cis-trans isomerism here. If I move to C, you can see that in C I have this compound where I have chlorine and a hydrogen here. But since I have 2 methyl groups on the other carbon, there's no cis or trans isomerism possible here. If we go to D, this is called an allene. Okay, this is called an allene here. And so the bond angle here is 180 degrees. And there's no way that there could be cis-trans isomerism here, because if you were to try to draw just like one of the carbon-carbon double bonds, like this, right? You've got a hydrogen up here and a methyl group down here. Then you've got a hydrogen here and a methyl group down here like this. But these are separated by 2 double bonds, so that's not cis-trans isomerism. So that's not an example. But B could exhibit cis-trans isomerism, couldn't it? Right? What if I had, what if I had one of the hydroxyls pointing down and the other one pointing up, like this, right? That would be trans. And what if I had the situation where they're both pointing down, for example, this, or both pointing up? Then it would be cis. And so it's B, the ring with the 2 hydroxyls that could be cis or trans to each other. Number 8 says, which Newman projection corresponds to point A on the graph of potential energy versus rotation around the carbon-2, carbon-3 bond of carbon-2, carbon-3 bond? Okay, so what's the molecule in question here? So this is butane, isn't it, right? We've got CH3, CH2, CH2, CH3. So this is for butane. So let's write that down here. We're dealing with butane. Okay. So if I take a look at all the minima, let's start with the maxima. Okay, so if I take a look at all the maxima here, these are going to be eclipsed conformations, aren't they? Right, so these are all eclipsed. These are all eclipsed conformations. And so A and B are both eclipsed. Okay, whereas the minima, these are the staggered conformations, right? A, and this is A over here as well. But anyhow, these ones are staggered. So staggered, okay? So C and D are both staggered conformations. Now what's the difference? Is that the other point, and I'll highlight it in blue, for example, this point here is also a staggered conformation, but it's even lower in energy. So if I compare C and D, which one of these would be lower in energy of the two? Is it C or D that would be lower in energy? Yeah, C is going to be lower in energy because the two methyl groups are anti to each other. Okay, so since there's anti, there's no gauche effects, and so this would be the lowest point, whereas D would be a minimum, right? But there is one gauche interaction, so that's going to make it higher in terms of its potential energy. And so this would be the answer. D, give me a thumbs up if you follow me on that one. And if you're like, boy, this is really reviewing some of the things that I learned in Organic Chemistry 1, which is totally the intention. I want to jog our memory of some of the things that we learned back in the day. You all passed Organic Chemistry 1, so let's move on from there. And let's take a look at 9. I'm just going to throw this out there to my students. They're probably faster than me. Could anybody answer question 9? What's the relationship between these two structures? Can anybody answer this one? Number 9. What would the relationship be between these two structures? Yeah, I think they're just constitutional isomers, aren't they? I agree with you. They're both constitutional isomers. Why? Because if you look at the first one, it's just a 6-membered ring, right? It's just a cyclohexane. You have one hydroxyl going down. You have the other hydroxyl going up like this. But if you look at the other molecule, you look at this molecule, we have a hydroxyl going down here, and then we have another hydroxyl going down here. So the connectivity is completely different, okay? They both have the same molecular formula, but different connectivity. So we'll put here constitutional isomers, and we'll put different connectivity, but same molecular formula. All right, let's move on to question 10, and this deals with nucleophilic substitution. It says which reaction would proceed faster? So we get a bunch of reactions here. We've got an ether reacting with hydroxide to produce ethanol and methoxide. So that would, have to be a nucleophilic attack on this carbon, and you'd have to lose the methoxy group. If we go over to B, you have hydroxide attacking this carbon, and you have the loss of the thiolate, sulfur with the negative charge, or mercaptide, whatever you want to call it. And then in C, you have this occurring, which is just insane, but anyhow, then you would lose a nitrogen with a negative charge as a leaving group. And then lastly, we have a hydroxide doing a nucleophilic attack on this carbon here, and then we're losing this whole group over here. So my question is to you, does anybody recognize this group over here? Does anybody recognize that condensed structure? Does it look like it might be related to something that you've seen before? Hey, thanks, Gilbert. 100% correct. It's a tosylate, right? So if we draw what Gilbert has identified, what he's saying is that you get the oxygen with a negative charge, right, to the sulfoxide, or sorry, the sulfone. So C6H4 is this part right here, the aromatic ring, and then you've got this. So this is a tosylate. All right, so with that in mind, could anybody tell me which one of these reactions would proceed the fastest? Or which one you think would proceed the fastest? Exactly, it's going to be D. Why? Because the tosylate is the conjugate base of the strongest acid, right? Toluene sulfonic acid, so TSOH, has a pKa that's around -5. So it's a really strong acid. Whereas the conjugate acid of methoxide is methanol, which has a pKa of around, I don't know, around 16, 17. We'll put 17. Then if you have the conjugate acid of the thiolate, so CH3SH, that's going to have a pKa of around 8. Okay, and if you have the amine, I mean, it's got a pKa of around, what, 38 or something like that? So if you have the CH3, 2, right, you have an amine that's got a pKa that's around, we'll just say it's around 40-ish, okay? So either way, you can see that this is the only one that's the conjugate base of a strong acid. And we know we have to have the conjugate base of a strong acid in order to have a good leaving group. So really, it's just understanding, what makes a good leaving group, and it's the conjugate base of a strong acid. And you know that toluene sulfonic acid is a strong acid, and that a tosylate is a good leaving group. Even if you didn't know the pKa of toluene sulfonic acid, all you have to know is what a tosylate is and that it is a good leaving group. So again, the C6H4, right, that just represents this part, right, the 6 carbons and the 4 hydrogens in that aromatic ring in the tosylate. All right, let's take a look at 11. It says, what is the expected product of this reaction? We're taking an epoxide, and if you remember, we looked at epoxide chemistry pretty early on in the chapter, or in the class rather. So the first step is that we're taking it and we're treating it with lithium aluminum hydride, right? So we have the aluminum hydride ion, which is a source of hydride as a nucleophile. So the question becomes, is the hydride going to attack this carbon, or will the hydride attack this carbon? Could anybody tell me which one it would attack? If I highlight, let's say, I don't know, this one in yellow and this one in blue, could anybody tell me which one it would attack? The nucleophilic attack of the hydride? Yeah, it's going to be on the yellow. Why? Because it's the less hindered carbon, right? But it's going to attack from the opposite face of the molecule as the epoxide, because the epoxide is pretty big. So the hydride is actually going to come in from the top face of the molecule, like this, okay? The deuterium is very small, and it's going to pop this down like this. Now I'm going to draw what you would get after that step. You'd end up with something that looks like this. Here's my 6-membered ring. Now my oxygen is going to be down here. It's going to have a negative charge. My methyl group is up like this. But since the hydride came in from the top, the deuterium is going to be pointing down like this, and my hydrogen from my hydride is going to be up on top like this. So what's happening in step 2? In step 2, you're just treating it with water and acid, right? So we're just taking it in step 2, and we're treating it with, I'll just write H3O+. Okay, that's good enough. Okay, and what's that going to do? Just a proton transfer, and you're going to end up with, let me just copy and paste it. That would probably be faster. So if we copy this and we paste it down here, you end up with this, and there you go. You end up with this alcohol. So which one of these is the right answer? And the answer is C. So you can see that it's really handy to be able to draw mechanisms to solve these kinds of problems and to understand the regioselectivity of the nucleophilic attack of the hydride. And we covered this at length in chapter 12, I believe. So there we go. Let's move on to question number 12. Just says, which of these structures best depicts the transition state for the reaction of iodomethane with potassium methoxide and methanol? So iodomethane is a great electrophile, right? We have iodomethane. We have methyl oxide or methoxide. What's that going to do? That's just going to do, we've got a strong base, strong nucleophile. We've got a primary alkyl halide that's going to react like stink. It's actually a methyl halide, so it's going to react even faster. But anyhow, what would my transition state look like? This is just a plain old SN2 reaction. Could anybody identify what would be the best representation of the transition state? Yeah, I agree. It would be C, because C shows the incoming nucleophile, right? And then the iodide is the leaving group, right? And what do we have happening? We have a nucleophilic attack, and we have a loss of a leaving group occurring here. And so that's definitely the best answer. In fact, all the other ones are pretty strange, especially this one. I really can't figure out what's going on there. But anyhow, there we go. Just recognizing a transition state. And of course, you know this reaction. This is the Williamson ether synthesis. Williamson ether synthesis. A real classic in organic chemistry. Let's move on to number 13. It says, what are the expected products from the reaction shown? We talked about this again in the alcohols chapter. So we have an alcohol, we have excess HBr. What do we do? What do we end up with? Could anybody make a suggestion here? Yeah, I think we're in the right vein. But remember, so I think that what's tricky here for students sometimes is that we have a cyclohexane, because what we covered is we said, okay, if you have an aromatic ring, okay, let's say you have an aromatic ether like this, where you've got an ethyl group like this, and you treat this with excess HBr, okay? Then what you would end up with would be the phenol plus the alkyl bromide, right? Ethyl bromide. But remember, that only occurs, like the only time this happens where the hydroxyl stays intact is when it's on an aromatic ring. So if you try it with cyclohexyl or ethoxycyclohexane, if you try the same thing, excess HBr, it's going to convert both of those into alkyl halides. This. And so the correct answer is going to be B, right? It's going to convert this into an alkyl halide. It's going to convert this carbon into an alkyl halide and this carbon into an alkyl halide. And so we have our alkyl halide here, here, and here. And so the answer would be B. Let's move on to question number 14. Identify the possible products of the dehydrohalogenation of trans 1-bromo 2-methyl cyclohexane. So if we want to do an elimination on this, right, if we draw a chair of this molecule, to try to squeeze it on here so we can see, but if I try to draw a chair like this, let me draw it like this. This conformation might be easier. So if I draw it, so that I have, I don't know, let's call this carbon number 1 and call this carbon number 2. So if I have the bromine going up, if I call this carbon number 1 and this carbon number 2, I have the bromine going up here, and then I have the methyl group pointing down like this. So this is my alpha carbon. This one in red, this is a beta carbon. And then this one over here in blue, this is a beta carbon, this one right here. So which one of these beta carbons can provide a proton for an elimination? Could anybody tell me, would it be the green one or the red one? I'll give you a clue. There's only one of them that could be abstracted for an elimination reaction. It's the one in blue. And the reason why is because this proton is anticoplanar, right? So then the hydroxide can come in as a base, can abstract this proton, you form the double bond, and you lose the leaving group like that. Whereas this proton that I'm going to draw in green, it's a beta proton, but it cannot be eliminated because it's not antiperiplanar. And so you would end up with this molecule. So I'll just draw it a little smaller over here, where you have your methyl group here, okay? And you have your double bond here. So that's the same thing as having the methyl group here and the double bond like this. And so the answer is you would only get A. You wouldn't get anything else besides that product. If you were to pull off the proton that I have in green, that would give you this type of compound, but that's impossible. And so you can see, since you can't form it, that none of these answers are possible. Only A is the only reasonable answer here. Oops, I kind of cut off a part of a molecule here, didn't I? Just down, there we go, like that. All right, we're taking something, and we're treating it with water, sulfuric acid, and mercuric sulfate, and we're making a methyl ketone. Does anybody remember what the starting material would be? We have 3 different functional groups, or sorry, 4 functional groups, and all 4 of the possible answers. Yeah, the answer is the alkyne, right? Because when you take this, excuse me, and you treat it with water, water, sulfuric acid, and mercuric sulfate, you actually end up producing an enol, don't you? Because this is a Markov-Nikov addition of water across that triple bond, but then this enol undergoes tautomerization to give you the methyl ketone.